Alright, let's kick this thing off. Otherwise, I will get distracted into having a lengthy conversation about animations based on Games Workshop properties, because I could easily be distracted into doing that a great deal if it came down to it. So I'm going to stop that before I go too far. Maybe... Oh, Chicken's already here. Chicken's visiting us early today. Maybe next time I do a casual stream with maybe with Dan Mansfield. Next time we do that, somebody came to say hi, so I thought I'd bring her up to the camera so that everyone can see her. Look, there we are. There's everybody. You can say hi to everyone. Okay. She'll just stand there for a bit. Hang on. Here we go. Yeah, maybe next time we do something like that, we can have a chat about all those wonderful things and hobbies and stuff that we get into. In the meantime, I wanted to get back into what we were doing, because we were looking at queues and we were building up the idea of what an abstract data type is. So the ability that we have to build up a type that has the majority of its implementation hidden from the code that uses it. So the fact that the implementation is hidden means that we are limited in what we can do with it, which means the only things we can do with the abstract data type is to call the functions that we can see in the H file that relates to it. And if all we're doing is calling those functions, it means that whoever writes the C file behind that, so for example, you're writing the C file behind the realm that is hidden behind the realm.h in your assignment, we can get a situation where we can actually have the code do exactly what is correct and never expose any of the inner workings in a way that might allow whoever's working on the main.c, for example, to accidentally access things incorrectly. So because from the main.c we can't access the struct itself, it means that we can't ever insert something into the queue in the wrong position. So we can't just put someone at the head of the queue when they've just joined the queue. There's only one way to add to the queue, and that will follow whatever rules the person who's implementing the queue has decided will happen. And usually when we have that decision, like if we work in a really simple team where there's two of us, one person's working on the main and the other's working on the C file, we get this combination between the two where the two people have initially agreed on what the boundary is between them in the H file and the kind of rules that they're both going to follow about using things, and then it's up to both people to just sort of implement everything so that it works. And so we got started on that last time, but we're going to finish that code today. I've got slides going on that as well, and we're going to look at another example. We're not really going to get much time to do much code for the other example, but we're going to look at another abstract data type called a stack. The reason why I'm using queues and stacks as opposed to just working with the examples we have, like the realm in the assignment, is queues and stacks are both actually things that come up a fair bit in computer science. So they're concepts where I can teach you what an abstract data type is and the idea of abstraction in general, but also teach you a little bit about the organization of data and how that's going to happen in the future as you continue playing around with data types. And so I'll talk about stacks actually, because stacks are really interesting, because stacks actually you've actually been using stacks the whole time you've been doing programming, because underneath the way that our code runs is actually in a stack. But we'll get to that in a second, especially with functions. So I've got some diagrams that show you all of that. So what did we cover last lecture? I don't know if anyone downloaded the slides already, but the classic mistake that I've been making all term is this here that says what did we cover last lecture. If you download it, it actually says what did we cover yesterday. So the yesterday joke is still going, and I might get to the end of term and get that one correct. So next week is actually the final week of lectures for the term. That's not the final week of the course because we've still got a few little things continuing on until the week after. Well, there's one not so little thing, which is the exam. And also stuff like labs and weekly tests will go just a little bit beyond the end of that week. I will do a live stream in StuVac. I'll want to do it early to give you the best chance of getting some support and lead up to the exam. So the exam being on Friday, I'll try to do it on Monday or Tuesday. Vincent, we still have a lab next week. In fact, next week's lab is quite useful because next week's lab will have a demo of the infrastructure that's used in the exam, and we'll have some past exam questions as well. So, actually, I'm not sure if they're going to be exactly past exam questions because now that we've got a take-home exam, the format has changed a little. So we might not actually have past exam questions. We might write new questions that are more similar to the way that we're writing the questions at the moment for the exam. So, yes, so the lab next week is actually pretty useful because as the revision lab, it's not just revision, but it's also like, okay, here's the format, here's how you will be working on the exam, and here's how you will submit the answers to the questions in the exam. Granted, if you've been going to all the labs up until now and doing all the lab exercises, nothing's going to surprise you there. It's going to be very, very similar. Okay, so last lecture, we did a recap of multifile projects because we've sort of seen multifile projects and have been using them a little bit in the assignment, but we've not gotten to the point where we can sort of, a lot of it was me just saying, okay, here's a multifile project, just use it. I haven't explained to you exactly why things are the way they are. But now that we're introducing abstract data types, you know why there's something like a type def. The type def is not very functional in a sense, like it doesn't do much. It just says two things are the same. But what it does allow us to do is it allows us as humans to look at something like it's a completely different new data type, like structs and new types. I mean, you could nearly consider an array of objects to be different from the variable type itself, but when we use the type def, it allows us to kind of declare something as a whole new word as a type, and then we can just use it like that rather than having to keep remembering that this thing is a pointer to a struct that I can't actually use. It's much better to see this something as something abstract instead of a pointer to a struct. And we looked at a queue and we said, okay, an abstract data type is a set of rules, and the only reason those rules are followed is because of the way that we implement the C file behind them. Otherwise, it has no rules. Like, otherwise the rules are just like, we wrote down these things and we agreed to do them. So if we agreed to do them, obviously we're going to want to make sure that the code we write follows the rules we've set out. So we started doing that, where a queue, the only rules are the first thing that went in is the first thing that comes out. If you remove something from the queue, you always get the thing that was the oldest. If you put something into the queue, it becomes the newest thing in the queue. And that's it. And so what we did was we set up an H file that said, okay, there's only specific ways that we can add or remove from this queue. And we haven't actually built a lot of that functionality into the queue yet, and we're going to continue that today. So we've got a couple of questions coming up there. Oh, Reese is sad about the assignment. It's a lot of work. It's harder than the other assignment, but you know, it's worth nearly twice as much as the first assignment. So you can take a lot of feedback from the first assignment and get a lot more marks than the second assignment. But it's also harder. It's harder because it's a culmination of a lot of work that we've done, as opposed to the first assignment, which was about 3 or 4 weeks worth of teaching that we were then testing. So it is, we've taught you twice as much. So we're going to test you on more stuff. Hopefully you're still at least enjoying bits of it, even if it's really tough. Because that's like the best way to go through life is to have things that are difficult and that challenge you. But you still know that regardless of how tough they are, there's still something you're learning from them. And you don't have to complete everything if you don't need to, you know. Yeah, and people saying it's much harder to understand why things aren't working. Yeah, And that's definitely the case because now we're in memory management and with pointers and things like that. So there's a lot more fiddly stuff going on. My advice is try to get some time with your tutors. I've seen that the labs still have plenty of time. You can, if you really need help urgently, email some of the tutors who aren't necessarily your tutor, but they have a tutorial coming up soon that you might want to sit in on. Because you could sit in on the tutorial in the lab, and then if they've finished talking to the students that are enrolled in that time, you may be able to like just ask them for questions because they're going to be there for the full 2 hours of the lab anyway. I'm not saying that everyone can just jump into any lab they want to. It doesn't really work like that. But if you get permission from the tutor, you can do that. Actually, one of the easiest ways to do that is to go to your tutor's other lab and see if there's space there for you to sit in. Terry's asking if Destroy Realm isn't necessary. Destroy Realm's still going to get tested. It's just that at some point we made a change and the leak checking wasn't working in the auto tests. But we're still going to be checking that you are destroying things correctly. Yeah. Tom's updating some information on that. There's going to be new tests in there that you want to check. In terms of like Destroy Realm, it's still worth a certain number of marks. So there's if you don't do Destroy Realm correctly, you're still not going to get the marks for it, even if the leak checking in the other auto test isn't necessarily working. The tests for that one are very specific, and they will actually be testing whether it's being destroyed properly or not. Yeah. And Matthew's asking you about auto tests for stage 4. Yes, there's much less auto tests for stage 4. As you get deeper into the assignment, you're expected to figure out what you're going to test for yourself. In terms of getting marks for the testing, you get marks for being able to test a lot of things. Not necessarily that you have to exactly meet the same specifications that we have in the auto tests for testing. Like if you've done good testing, you'll get marks. Even if it's not exactly, because it's not like functionality. Where we're building functionality, we have exact reasons why things should be the way they are, and we'll test you to see whether you've implemented the specification. When you're doing testing, it means you're just trying to catch a lot of situations where things could go wrong. And so different people are going to write different tests, and they're going to catch different things that are wrong with things like our half-broken solution that we're going to be testing you against. So you're going to get people writing different things in their testing and still getting the same marks. You can completely miss something that someone else gets, but you could catch something that they didn't, and you'll get the same mark. So it's not like the implementation of the assignment, which is really clear-cut, exactly what you have to do. Testing is more vague, because there are so many different possible problems that could happen. If you can pick up some of them, if you can pick up a good amount of them, if we can see you've put a good effort into it, that's how you get the marks for the testing. Also, if you do hit later stages, like stage 4 or 5 and stuff like that, and things aren't working that well and they're very difficult, you can consider that you don't really have to do those. You know, so you can hit that point and go, okay, I could put myself through a whole lot of pain to get 5 extra marks in this assignment, which might equate to like 1 or 2 marks to your total final mark in the subject. Or you could be like, all right, let's go study for the exam, let's go work on something else, let's learn something new instead. So I think there's a point where, and this is something else to learn, which is really important, there's a point where you decide when you're going to finish what you're doing. And where you're going to tie it off and say, all right, at this point, I don't think there's anything more I can do with this. I'm going to go back and I'm going to make sure everything's clean, everything's looking good, everything's running nicely and stuff, because there's more marks in the fundamentals than there are in the bonus bits. Okay. I'm going to let Tom and Dean answer questions there about the assignment, because I've still got content that I want to talk to you about. Okay, so we've got our cues. And today we're going to finish the queue implementation, which is more than just the destroying and freeing. I think we weren't even adding or removing items by the time we finished yesterday. And we're going to look at stacks, which are another abstract data type. So I'm going to jump pretty quickly into our code here. I've got a recap here in the slides, but I don't think we necessarily need that. So we're going to add a main file to use the queue. I've actually already added one. And we're going to look at the code that we're looking at for adding and removing to the queue. So we had some slides here about adding to the tail. So adding to the tail was, we had the tail object and a new object. And we were going to get the tail's next pointer to point at the new object, and then the new object can point at null, and then we move the tail pointer to move to the new end of the queue. So where are we? Here. Okay. Did a little bit of setup in advance for VLab. So the way I've done my directory structure, I've made a directory for queue and a directory for stack. Because we're going to do the stack in a second, I just copied some of the files in advance. Those files are available in the lecture section on the website if you want to code along with me, or you want to just follow along while you're looking at the code. Okay, so in the queue here, I've got 3 files. So the q.h and the q.c are the same files we used on Tuesday. The main.c I've added in. So let's have a look at all of these. I don't know if you've seen the trick before that I use for gedit. If I want to open all of the files, I can just put a star and it'll grab all the files in the directory. Which sometimes doesn't work because it tries to grab files that aren't readable files. If you've already compiled stuff in there, doing gedit star will also try to open the executable files, so you just sort of have to close those. So here is a main file that we could use, and it's a queue for ice cream. So what it does is it prints out the queue for ice cream, and it says create a queue, so it's including q.h, so we can use the queue functions. Creates a queue and has a number 1, 2, and 3, and it adds people to the queue. We haven't implemented queue add yet, so this file is not going to help us yet because we haven't actually implemented the back end of what's going on. So what we will do is we will continue where we left off here. So we said that queue add was going to create a new item, and then it was going to move the tail pointers next to aim at that item, and then it was going to change where the tail pointer itself was pointing at to point at the new item. And so I said we could do a helper function here, a static helper function. So static means it's only within this file. Don't worry too much about static. It's something that is kind of handy to know about, but like we are actually getting pretty close to the end in a sense in COMP1511 because we're in week 9 out of 10. This, in fact, abstract data types is the final topic. Like, I'm not going to be introducing any more material after this. And even abstract data types are not going to be assessed super heavily because you notice that as much as they are in assignment 2, we built it for you in assignment 2. So there isn't really any point in 1511 where we'll ask you to build an abstract data type from scratch. We may need you to understand things like what a queue is and what a stack is and what their purpose is, but we're not necessarily going to ask you to build this whole thing in this week's lecture that I'm doing. Okay, so I created a helper function here that could create a single node. So in terms of creating a single node, that's going to be a memory allocation. So we're going to memory allocate for a queue node. So my malloc is going to be size of struct queue node. I'm going to want to retain a pointer to this. So I know that this is going to be a queue node pointer. I'm going to call it new node is this. Okay, so this memory allocation code is the kind of thing that we've seen before, and we know pretty well now that if we want to memory allocate something, so we want to use the malloc command to memory allocate, we will tell it the size of the type that we're going to use, and the type is a struct queue node. Malloc will return to us the address of the memory that it's just created, and we store an address and a pointer. So we have a queue node pointer, a struct queue node pointer called new node. So new node is a pointer to this memory that we've just created. We then want to populate this with some data. So we know that new node has a data field, and we know that because we have access to the struct in this file. It has a data field, and that's going to be set to whatever data we were given as input. So note that these two data are actually different, even though they're spelt the same. One of them is the field inside the node we've just created, and the other one is the input variable, the temporary variable that we have. Well, it's not really that temporary, but the variable that we have inside this function, which was given to us. So you can use the same name here because this one is quite clearly, oops, I don't want to move that, is quite clearly inside this node. Okay, the other thing that we want to do is to say that the next of this, because if we just malloc the Q node, it's going to have some kind of information, uninitialized information in both of these variables, so we want to initialize them both. At the moment, we don't know what the next of this node is going to be, so we're just going to make it null. So this way I've set up a really generic node that is not yet connected to anything, so it has a null. And then we can say, all right, let's give back new node, and we can say, okay, create node is able to do all the mallocing and setting up of a new node here. So I can call create node then, and I say, what's the value that's going in here? I got told that the value here was the variable item. So item is the value. This thing's going to give me back a QNode pointer, a struct QNode pointer. So I'm going to want a struct QNode pointer. And I'm going to call it, add node because it's the node that's about to be added. So that variable name should remind me that this node is going to be added to the list. So I've now gotten to this point here where I have a new object and I put all the information I need into it. In fact, I've actually got this bit already with a new object's next points to null. So it's already ready to be the tail of the list. It just needs to be connected to the list. So we're in this separated situation here. And then what we're going to do is we're going to add this pointer here, where the tail's next pointer would normally be null. Now we're going to change the tail's next pointer. So the tail points at this object, the final object. Its next pointer always points at null because the tail's aimed at the final thing in the list. Now we're going to point it at the new object instead. Okay, so I have a Q here that was given to me. The Q is a Q internal struct, which has a tail. So Q's tail gives me the final node in the list. And I say, what is the next of that final node? It's going to be aimed at null, but I want to replace that with the pointer to the new node, which is add node. So what I'm doing here is I'm saying Q tail next here. This is the whole Q. This is the tail pointer in here. Its next is this, and I set it to the address of the new object. So I turn this pointer null into this pointer that aims at this object. The next thing I want to do, because at the moment tail is now pointed at the second last object, not the new last object that I've just added. So I want to say now the tail itself. So now I'm not moving the next pointer of the tail. Now I'm moving the tail. So this pointer was pointing at what should be pointing at the final element of the list. So if I wanted to point at the final element of the list, I can say, okay, now set the tail to this. So what I've done is I've basically taken two pointers and aimed them both at this new node. So one was the pointer from the final element of the list. So this was the tail's next. And then the pointer that used to aim at the final element of the list now aims at the new final element of the list, the one that we have just added. Okay, so what we have here is we've created a node, we've added it to the tail, like so. So there's only one issue that we might get into here is, let's look at when we created a new list. So we created a new list and the tail was null. So if the tail was null, if there was no final element of the list, we can't just go look at the next of an element that doesn't exist. So let's actually test this, and we'll watch this blow up, and we'll see this happen. So I'll just clear this. Okay, so I'm going to compile. And remember, with multi-file projects, we're going to compile all the C files that we're going to use, but none of the H files. So we're going to go main.c and q.c. And our output is going to be called, I'll call it QDemo, the program. Ooh. Okay, main.c20, undefined reference to QRemove. You've called QRemove, but it doesn't seem to be implemented. Ah, okay. So it says main.c called QRemove. QRemove has something here, but since we don't have any QRemove implemented here in our C file, my compiler says you're calling a function that doesn't exist, so it'll never run. So for the moment, I'm going to get rid, well, I'm just going to comment out my QRemove, because we are going to use that later once we've implemented QRemove. And so this means if we never call it and it doesn't exist, maybe it'll be okay. So let's compile that again. Okay, we're able to compile. Whoop. Apologies. I just hooked the cable for my camera and yanked it off the desk. I hope everyone's okay. I hope that wasn't too loud. I apologize. Everybody fell off my table. Okay, so I've compiled this. Sorry, everybody. Let's run QDemo. So let's look quickly at what QDemo is going to try to do. It's going to try to add 3 elements to the list, and it's going to let us know what it's doing. So it's being very verbose, as in it's talking a lot about what's going on. And so let's see what it's able to do. So I'm predicting that it will do some things, but it's going to get stuck at some point. Sorry, everyone. No, that was just me. The cable is hanging off my desk. So it's hanging a loop off my desk, and I just hit it with my knee and just yanked the whole camera. So, yes. Let's see where we go. Okay. Creating a queue for ice cream. Person 1 joins the queue, which is here. Person something joins the queue, and then we called queue add. Runtime error, accessing a field via a null pointer. Queue tail next equals add node. So that's where I thought it would be. Let's have a look at that. We called queue tail next when tail was null. So we went to the queue here. We went to its tail pointer there. Its tail pointer was null, and we said go to next. And it's like, hey, this is a null pointer. There is no next field on a null pointer. Even if that pointer could theoretically point at a queue node, because it is not currently pointing at a queue node, there is no next there. So we need to be careful here and say, all right, if the list is currently empty, we need to do something different. So let's say here, if something, and this time I'm going to remember to put an else here. I think I'm only going to want this bit in the else. Okay, so my if here, I'm going to fully document this. So I'm putting a lot of comments in here. This is more comments than code usually needs, but when I'm teaching you things for the first time, I like to comment it really clearly so that you could go through this code afterwards without me to explain it, and you'd still get all the information. Just looking at the comments, everyone's like scared of everyone with that. Yeah. Michael's asking about a doubly linked list. I think Dean is answering that question there. Yeah, and Kyle is also. Basically, a doubly linked list, the question here, is a linked list that doesn't just have a pointer to next. it has a pointer to previous as well as a pointer to next. And then if you have something connected up where it's all connected multiply, it means you can go in either direction. It's possible. They're quite useful. They're more complicated. So the reason why we're using single linked lists at the moment is that everything we're just doing is in the simplest form we possibly can. And as we've seen the conversation earlier this lecture as well, just about how difficult the assignment is. If we added another layer of complexity to the basic structure, we would just cause more problems. So I think I think we want to keep this as simple as we can until we get a good grasp of it, and then we'll start building up complexity. Yeah. Okay. So if I'm asking if the queue is empty. So if the queue is currently empty, that would be if tail, the queue's tail is null, then the queue is empty. Which means what we would do now is we wouldn't attach the new node to the next of the tail. Because if there is no tail, we have no next. So what we actually end up getting is if the queue's empty and we're going to add something to the queue, that new object becomes both the head and the tail of the queue because it becomes the only object in the queue. So I can do something like this. Queue head is equal to the add node because if it's the only thing in the queue, it's the first thing in the queue. And funnily enough, queue tail is also pointed at the new node because if there's only one item in the list, it is both the start and the end of the list. Oh, hang on. QTail's add node is there. I don't need to do that. So this just says the head becomes the new node. Otherwise, if you're not the only item in the list, you get attached to whatever was the previous item in the list. No matter what happens with this if-else, the thing we've just added is always going to be the last element in the list. So the tail pointer gets pointed at the new node that's just been created. So I think that's the only thing that we need to do here. So if the queue is empty, the new node becomes the whole queue. If the queue wasn't empty, then the new node gets attached to whatever was the last node in the queue there. So if I save this and we try this again, so let's compile this and run this, I should get, okay, I get something that says everyone's joined the queue. I don't know exactly whether this has all worked because I haven't actually pulled anything out of the queue yet to see whether I'm getting the right things, but I think that this is probably okay. Okay, so that's our adding. Now let's think about removing. So adding was adding at one end of the queue. So we always know that if it's a first in, first out, if it's a queue, people join the queue at one end and they leave the queue at the other end, right? So same thing, if you're queuing up to I don't know, get on a bus or something, whoever's at the back is the last one to get on, yeah? So, what is it, chicken? Yes? Yes, I'm teaching them about removing from the queue now, and how they can only remove from the head of the queue. And she's checking up on me to make sure that I'm teaching her properly. Okay, so the head of the queue is the oldest object in the queue, which means the oldest object is going to be removed from the queue. We're going to do a normal removal, the same kind of removal we've been doing before, but it's really easy because we're only removing the head of the queue. So if I'm removing the first element of the queue, the head pointer is going to skip that first element of the queue, and then we're going to free up the object that had been there. So we've got some code for this. I'm just going to write the code rather than looking too much at what's there. So I'm just dragging this over here. I'm going to take my queueRemove function here, and then I'm going to make some space for myself to implement this here. So removes the item from the queue that has been there the longest. freeze the memory used by that Q node and returns the data. So we're just going to give back the number and yes. I'm just going to put her on my lap because she will interrupt us less if she has somewhere to sit. Oh no, she doesn't want to. Fine. She's over here at the moment, mildly angry about things. Okay, so if I want to remove something, I'm going to do something reasonably simple where I'm going to have the head pointer skips the oldest node. Actually, before we do that, we can't skip the oldest node before we've actually gotten the information. So get data from the node, then we skip the node, and then we say little bit of chicken, just for fun. I think she's a little grumpy today. I'm not sure why exactly she's grumpy, but she's a little grumpy. Okay, so the head pointer will skip the oldest node, and then we will free the oldest node's memory. Okay, so to get the data, we want to store that in an integer, which we're eventually going to give back. So int, I'm going to call it rem data, as in like the data that's of the thing that's about to be removed, is equal to Q's head. So the Q head is the first node in the queue. So the Q's head's data should be the number that's inside the head of the queue. So when we start using the multiple arrows, I like to try to think clearly about where these pointers are going, and think in my head about what's going on here. So Q is the queue itself. That's the queue internals. Queue internals has a head pointer inside it. So I can say, okay, go to that head pointer. That takes me to a node, and I can go inside that node here and look at the data. So that's going to give me the number that's inside the first element of the list. And I can say, okay, this is the data that's about to be removed. So that's okay. That's good. I can then skip over that node. Now, to be careful with this, in order to skip over the head pointer's node, and I still want to free it, I need to keep track of what the head pointer was. So I'm going to need two. I'm always going to need 2 pointers if I need to keep track of something and move another one along. So I'll call it rem node because it's the node that I'm about to remove. So I'm going to keep a pointer called rem node. Oops, not writing C right now. It's a Q node pointer called rem node. So this is going to be pointed at the oldest node in the list, which is the head. So I can say the queue's head, copy the queue's head here into a pointer. Then I'm going to skip that node out of my list by moving the head pointer along. So I'm going to say the queue's head. So let's go back to my diagrams here. The queue's head here was pointed at this node, but now I want it to point at this node. This node is the next of this node. So I'm going to say that the queue's head will now be the next of what had been the queue's head before. So it's a pretty confusing line of code, but it's actually this. It's not that much different to when we were looping through a list and I said current equals current next. But now we're now just one layer further away. If we say queue's head is now equal to the queue's head's next. So what we do is we find out what's next from the previous head, and then we replace our head with what was the next there. So this is just moving the pointer one further along in the list. Well, lots of questions there, but I think Dean's answering most of those, so I think it's okay. All right, so what we've done there is we have kept the data, kept a pointer to the old head, moved the head pointer along to the next one, and now we can free rem node. So note that we could not free rem node here once we'd figured out what rem node was, because here rem node is still pointing at Q head, and if we free it there, then we try to use it by trying to get to its next. That would be what's known as a use after free error. So we tried to use a piece of memory after we'd freed it, which is super dangerous because we don't even know if we still have access to that memory or not. So only after we finish getting all the data we need out of this thing do we then free it. Okay, so this should be able to skip over things, and now we should be able to remove things from the queue. So let's just clear those little errors there. Just going to check if I saved that. I think I did. Yeah, okay. So we go and, oh, actually, before we do this, we want to actually test this function because I commented it out a second ago. So let's try removing items from the queue. Uh-oh. My VLab has just stopped responding. Let's see if my upstream... Oh, my stream is still upstreaming perfectly, which means my internet connection is fine. Oh no, my VLab is running. I think my connection to VLab is fine, but it just sort of... Look, everyone else on VLab right now needs to stop using it because we're using up too much of the processor and I'm not getting enough. I kid. You can use it, it's fine. It's probably just something happening in the background because VLab's just a whole bunch of virtual machines and stuff like that. Oh, everybody had the same thing with VLab just then at the same time. Okay, so that was probably something happening in the background. Yeah. I mean, it's tough because VLab is trying to serve information to probably hundreds of people at a time, and so I don't know how well the uni's internet connection always deals with that. Okay, so let's try removing things from this queue, and I'm not sure this is entirely going to work. I just want to test it and see. Oh, whoops. Warning, unused variable rem data. So where's my rem data here? Int rem data. Well, that's a really good warning to get because I'm supposed to return an integer here, and I didn't return anything at the end of my function. So let's return rem data, which is going to give back information to the main to say, okay, this is the number I just removed. Okay, let's try compiling that again. And also we got a warning here saying a non-void function does not return a value. So it was like, okay, you appear to have forgotten to return something. Compile that. Alright, we are compiling now. Go back to running it. Oh, it does work. That's not too bad. So person 1 joined the queue, then person 2 joined the queue, then person 3 joined the queue. Then person 1 got their ice cream, then person 2 got their ice cream, then person 3 got their ice cream, which means that everyone joined the queue in a specific order, and then everyone was served in the same order that they joined the queue. So I know that my queue rules are being followed by the implementation that I've built. So everything was getting added to the linked list, and then the removal from the linked list was taking things from the start of the list and onwards. So not too bad. We've got something going here, which is working. I show you a way that we can break this, though. And this is the kind of thing you can think of when you're doing testing and things. Come on, VLab. What's going on? What if... What if I try to remove 4 things from a queue? So let's try this and see what happens, because when I'm in this situation, there's really not much I can do. If I try to remove something from a queue, and it has no elements in it. Um, QRemove is going to give back an integer, and there's no integer in my rules that is off limits. So I can't say, okay, what about a 0? Is that off limits? But what if there was a person 0, a patient 0? Sorry, I just love like all the terminology around pandemics and stuff like that. Or you know, what if I say, okay, negative 1,000, but like what if someone wants their signifier for who they are to be negative 1,000, right? So there's no specific integer that I can give back here that's actually going to say this QRemove didn't work. So let's try running this now and see what happens if we try to remove from a queue that's currently empty. Yep. We just have a problem, right? So we've crashed because we're trying to access a pointer that's null. Because after we removed the last element from the list, the head would have become null, because the head would have moved on to the next of the final element that was removed, and the next of that was null. So we end up in a situation where the emptying of the queue leaves us in a potential situation for our program crashing without a good explanation. And so if we want to, we can crash with a much better explanation here. So let's leave this in here because we still want to test this, but we want to make sure that if we can't remove something from the list, so if the list is empty, so if the head is null, we would consider the list as empty. The issue here is we can't give back a number that makes sense right now. We're actually in a pretty bad conundrum. We cannot give back a number that makes sense, and the only option is to crash the program. So if you go back way back to like week 3 or something, where we didn't know much about programming yet, but I was talking about, okay, how can we deal with this situation in a way that's going to give the user useful information, but not allow this program to operate incorrectly. I'm going to use that kind of solution here. So I'm actually going to, let's start with a printf. Oops, printf. Yes? Somebody's very hungry today. If I want to do a printf, I'm going to need our old standby standard input output. And what I'm going to say is attempt to remove from an empty queue, program will exit. Because it just can't deal with it. Like, when you think about it, there's nothing that we can do here because we have to give a number back. So we can't just give a number back that doesn't work. We're actually going to kill this thing entirely. So let's see, did we... I'm trying to think about the code. Yeah, we're using exit. So there's actually a keyword we can use here that will quit the entire program. So this can basically short circuit going all the way back to the main and forcing it to return, and we can make it an exit 1, which is different from a 0. Like when we return 0 from a main, that means everything's good, situation normal, that kind of thing. But if we say exit 1, that means there was a problem. And at least we've said to the user, to the human user, what the problem is. So let's see if we get a better response this time from the removal than we did last time. So I'm going to compile that again. Oh, if head equals null. There's no such thing as head yet. It's the queue's head. So this is me thinking abstract about things and just going, oh yeah, there's the head of the list. But if I don't say exactly which queue I'm looking at for the head, I'm not going to be able to just read head. This is one of those times where humans understand exactly what we're doing, but we need to actually specifically say things for the computer. I make mistakes like this a lot, right? Because I'm just abstract thinking about the algorithm itself, and I forget that the computer wants a specific path of which pointers to follow to get to that particular thing. Okay, so now it's compiling. And we do this queue demo, and it's going to, okay, now we have a sort of a better resolution to what's going on here. 3 people joined the queue, and then we tried to remove 4 people from the queue, and the attempt to remove from an empty queue caused the program to crash at that point. But it's not just crashing, we're exiting a bit more gracefully at that point, which is nice. Okay, so we've got our test code here. This is the same code that's in our main. So let's look at making sure that if, let's say, for example, the shop closes, and there's still people in the queue, we have to say, sorry, you all have to go home. We're going to free the queue. The thing that we're going to do here is probably just make use of the fact that we have pointers already for things, and then we're going to, just a second, little OCD thing there. I got to change that. It just had no syntax highlighting in the slide. So we're going to go through and we're going to have a removal pointer, and we're going to move our head pointer along through our list, and then we're just going to free everything in the queue. So this is not very different from the freeing code that we used before for generic linked lists, but this is going to make sure that we're freeing all the memory in the list that we're using. So queue.h had a function called queueFree, which is going to take a queue and free the whole thing. And so we're going to create that function here. I should say one thing. You don't have to do any specific order between the H file and the C file. So the functions in the C file don't have to be in the same order as the H file. They're all compiled somewhere, and then when the H file is seen, it links up to the things that that have the same name. You may notice every now and then when you get errors to do with H and C files that it will say linker error. The linker is part of the compiler that joins up things that have the same name. So they can find each other no matter what. But for humans, I like to do things in exactly the same order in the H and the C file. So someone can look at the H file like the table of contents, and then look at the C file, which has a lot more code in it, and still find things because they're in roughly the same order. I say roughly because there's still static functions and stuff, helper functions. But you'll notice from the helper functions that I specifically put them in what you can think of as an appendix here. It's after all of the functions that we're going to use there, and separated. So that's the way I like to do it. You'll notice that the assignment is kind of set up that way as well. It's pretty common standard for what people use. So my free function here will free all the memory used in the queue. So what I'm going to do is loop through. So if I'm going to loop through to the end, I'm actually going to use the head pointer, and I'm going to loop through using the head pointer. So we'll keep looping until it's null. If it's null already, then we don't have a problem because we don't have anything to remove. And then what we're going to do is move through the list, keeping one pointer behind us, basically, which is going to be the one that we're going to remove, and we move the head pointer along. So I know that my moving along is going to be the queue's head is equal to, oops, queue next. The queue head's next. So this is the same thing. Basically, the queue head is the looping node. Sorry, the looping pointer. And this is the pointer. The head pointer is now going to move through the list. So this thing is going to just move me through the whole list like this. But every step along the way, I am going to make a new pointer, queue node pointer. I might call it rem. No, oh wait, it's not rem. It's a free node. And that's going to be whatever the queue head is currently pointed at. Then, once I've got this free node that I'm going to free, I will move the head pointer along so the head pointer is no longer worried about what the free node was, so then I can free it. Let's see if I did the code the same as there. Yeah, cool. Okay, so questions for everyone. Feel free to ping chat if you want to. Have I done everything I needed to? Will this free all the memory that I use in the program? You can say yes for it will free everything, or no, it will not free everything. So you don't have to have a full answer if you don't want to. You can just have a one-word answer. So there's a few people who are already like, it's behind you! They figured it out, right? As someone just said before, Terry was saying equal and opposite force, right? Yeah, he's behind you. No, because every memory allocation must have a free. And what I was doing here, yeah, see, chicken knows. I don't know if you can see that little paw there. Chicken was letting me know that there was a problem there with what I was doing. Oh, Liang said try it and see. So if you're not sure, if you're not happy to say yes or no, you can always just test this. So let's do a quick test. Leak check. I think that's how it's spelled. Oh, hang on. I need to call the function. I'm trying to test something that I'm not even calling. Okay, let's take out the line that was going to cause it to crash. And let's say, I think it's called queue_free. Yeah, queue_free of the queue we're currently using, called ice queue. Because it's a queue for ice cream. Oh, she's standing on my mouse. Okay, we'll try to free the queue and then see what happens. So we'll compile this with leak check. Did I save that? I did not save that. And we'd probably want to test this with a queue with some elements in it, as well as testing this with a queue that didn't have elements in it. You'll notice nowadays that like we've gone to this point with programming where I'm saying a lot more about how I test what I'm doing. So you can see what I'm doing is like, okay, I test adding things to the queue. Make sure I test adding multiple things to the queue. I test removing the queue down to nothing, and then I test removing past nothing. So I'm trying to give you clues about what kinds of things that we do with testing. We test the ends of things, like is something full, is something empty, has something have some partial information in it. There's always weird differences between whether something has one object in it or 0 objects in it and how they behave. And so all of this stuff I'm doing by recompiling and checking it again with different kinds of inputs and stuff is the kind of thing that I'm trying to just sort of slowly slide into your thinking about how we make sure our program's doing everything that it could do. So here's the leak check, and we'll run it again. Error, free not called for memory allocated with malloc in function queueCreate at line 27. So a lot of people already knew this, and that's good. I'm glad you're watching everything that I am allocating to see what I need to free. Line 27 is here. Malloc queue internals. So we freed all the nodes, but we did not free the queue internals. Although we should probably test this with some nodes still in it. So we'll leave 2 nodes in there, and we'll do another leak check just to make sure that we're only leaking memory from the queue internals. I'm pretty sure of that, but I prefer to have concrete tests rather than pretty sure. Pretty sure is just how you introduce more bugs into your program. Okay, so yes, line 27 is the only free not called so far, so I think that's pretty reliable there. So we need to make sure that we are also freeing the queue itself, because this queue here is pointed at its queue internal. So after we've removed the list, now be careful because you cannot do this in the opposite order. I can't free the queue internals first and then go through the list, because if I free the queue internals first, I'm going to lose these 2 pointers, which means I'll no longer have access to the list. So it's much easier to free everything inside something and then free the container afterwards. Subtle, not very subtle hint for how to do part of stage 3 in the assignment there. Okay, so I freed everything inside the container, and then the container, let's check if that worked this time. So we'll compile with leak check. Check this. Alright, we're not getting leak check coming up with issues anymore. So we're being able to add and remove and clean memory. Is there anything else in the queue? Oh, there was queue size. So, alright, here's the stuff about testing for memory leaks with leak check and stuff, and here. Yeah, so I had all the slides for it. It's -- leak check. I think that's it. UG, it's, hang on. Ugh! You're right. Error in the slides. Thank you for that. You know what? I'm going to change the font of that one so it actually looks like something that was typed in. Yes. I went through these slides quite carefully as well, but obviously not. I left a whole bunch of stuff in there. Oh, both works? Okay. I didn't realize that you could do it without the hyphen and it would still work. It was probably why I had it typed in there, because I've been using the other version and it was fine. Okay, so now we can free all the memory. So there's another thing that we might want to do. Oh yeah, right, so your tutor taught you the other way. But whoever wrote DCC, this is Andrew Taylor saying, okay, people might spell this a different way, we'll just accept both. And so here's me thinking it's only one way, and the tutor's thinking it's only the other way, and it's actually both, which is nice. It's always nice to have, like, it accepting all of our options rather than rejecting some of them. Okay, so I want to quickly run through one other thing. So I want to go on break with the queue finished, and after break I'm going to move on to the stack. So I'm just going to keep going for a little bit here. Okay, so let's think about the number of items in the queue, because we could get a nice benefit out of this. If we always know how many people are in the queue, we will always be able to protect ourselves against removing someone from the queue, well, trying to remove an item from the queue when there's nothing in the queue, right? So we don't want to remove nothing from the queue. We want to, if the queue ever gets down to 0, we want to just not call the remove function. So a nice thing to do would be to look at the number of items in the queue. So we could have a function that says, okay, how many items are there in the queue? And this function could have a counter, loop through the queue, and add 1 to the counter every time it loops through the queue, right? So that's a very, very simple way that we can just do one loop through the entire queue and know how many items are in the queue. I think add location does that. Who knows? But there's always, you know, like count how many things are in something. I could, if I wanted to, do this. However, let me be trickier. Let me be trickier with this, because there's a more interesting way for us to know how many items are in the queue. So, if I want to be trickier than this, oh, hang on. Let me just shrink myself a little there so you can see all the words. We have a queue internal structure that can store how much information's in the queue. So what if, instead of counting it every time someone asks, what if I keep track of it? Because the size of the queue is only going to change when someone adds or removes something to the queue. So all I need to do is say, here's the size. Oh, chicken. Somebody's very hungry. I don't know if you can hear that in the background. I think you probably can. So let's track the size in the queue internals, and every time it changes, we'll just change that number. And then if someone wants to know how big the queue is, I just give them that number. And it's much easier than then going through the whole list and counting how many things are there. Loud and clear. Okay, so let's add this variable to our queue internal structure. Size. And we know that if we create a new queue that has nothing in it, then the new queue size is 0. If we add an item to a queue, then the queue size goes up by 1. So I'm just using the plus plus to add 1 to the queue size. If I remove an item from the queue, let's do it as the last thing. Update size of queue. I probably didn't need to. Some comments are not necessary. I mean, it's going to be like update size of queue, and it's like queue size plus plus, which is like literally the same thing. I mean, if you know a bit of code, you know that I'm updating the size of the queue. It's not plus plus. We're removing an item from the queue, so it's minus minus. Now, I have an integer that's tracking how many items are in the queue. Starts at 0. We add 1 anytime we add something to the queue. Here, we remove 1 every time we remove something from the queue. Which means, now, if I have this question about queue size, this turns into a really, really funny function. So this was the last function. Return the current size of the queue. Check out this function. Super big brain programming right here. That's it. That's all I have to do for the size of the queue, because I've been tracking this integer every time I did anything. So I created the queue, starts at 0, adding anything adds 1, removing anything minus 1. So all I need to do, if someone wants the size of the queue, I do nearly no work at all. I just go, look, I'll just access it and give it to you. You want this value? I've got it. I've been doing little bits of work all along the way to increase or remove or reduce the number of things in the queue. So now we can be a little bit, I'm going to delete these entirely. We can do something more interesting here, where we can say, I will service the entire queue. So I don't know how many things are in the queue. I can just say, I'll service the entire queue. So what I'm going to say now is, I have a function to tell me how big the queue size is. So if queue size of my ice cream queue, called ice queue, is greater than 0, then I will serve a person. So I'm going to Control X that, Control V there. And I think I don't need to do anything to this line. Yeah, because queue remove is going to give me back their number there, and I'm going to serve them. So now I am not going to need to worry about crashing this program, because I'm only ever going to try to remove something from the queue when it has something in it. Priya was asking about having a look at queueCreate. So queueCreate is now initializing all of the variables in queue internals, which allocates the queue internals and says, because it's empty at the beginning, the head doesn't point to anything because there's no objects, tail also doesn't point at anything, and the current size is 0. So what we do is we take everything in queue internals and we set them all up as zeros in a sense, and say, okay, here's your new queue, and then you can start working with it. So let's test this. I'll leave the leak check on, just in case I've caused some issues somewhere. And I'll run this. Person 1 joins the queue, person 2 joins the queue, person 3 joins the queue. They are served in the correct order, like so. Everything's cleaned up at the end, and that is our complete queue example. So that's a really simple implementation of a queue, because I mean, like, we only spent like 2.5 hours on this. So obviously it's not at, you know, your assignments, you're spending like 10s, 20s at least hours on those. Well, I hope, because we put a lot of work in there so that you'd get a chance to practice a whole lot of things. But at least you can see this example of, we've got this H file that says these are the things it should be able to do. And what we do is we go through, we implement them one at a time. And we chose a linked list to do this. So a challenge. I haven't issued you a coding challenge for a long time. And obviously I don't expect a lot of people to take this up because you've got an assignment to do, and that thing's worth marks, where this isn't necessarily. Yuji's asking why Q.C is not uploaded into WebCMS. It's because we haven't finished it yet. I'll upload it now after we're done. Well, after this lecture, I'll upload it. But could you implement Q.C using an array instead of a linked list? Because you definitely can. There's definitely a way to do that with an array, because the underlying data structure was never part of what the queue was. The queue is an abstract concept that says whatever went in first gets removed first. That's all. So if you wanted to, you could do this as an array, and you could track the positions in the array or something, or you could use it as an array of structs where each thing has a timestamp of when it went in, so that you know which thing's the oldest. There's lots of different ways you could do this. But I leave that as a challenge because it's an interesting thing, because after the break we're actually going to look at some of the ideas of implementing something in multiple different ways. Okay, let's go on break. Yes. I have some stuff here. I don't want to spend too much time talking about it. Actually, you know what I'm going to do? I'll make that as big as it can, and I'll do the chicken feeding on the camera while I talk about what's here. So you can go on break if you want. What I'm talking about here is a little bit about, more thinking about programming, because we're getting to the point where I'm not going to be talking to you very much anymore, because you're not going to be in my course. So I just want to talk about the future a little bit. But I'm going to go get Chicken her food, so we'll just go on a break scene, and I'll go get Chicken her food because she really, really wants it tonight for some reason. And I'll talk about this while she's eating. Okay, back in a sec. I thought you might enjoy this because the amount of sound she makes in the lead up to eating is hilarious. So let's go get her food. It's food time. There we go. Alright, chicken's eating. Hope you can still hear me, because I know the microphone's not aimed at me anymore. So I was going to talk a little bit about, where are you going to go from here with your programming? Because there's lots of things that we can do from here, and the thing that we want to get to eventually is where you don't need someone like me anymore to teach you about programming. You can learn for yourself what you want to do. So the idea is, where do we go to go beyond course content? So there are places that you can look for things. Stack Overflow is one of them, and Stack Overflow is a really famous one. Someone says they have a fan base for me.
Do I have stands? I've always wanted stands. I need to get a special name for my fans, because I just recently became a Blink, who are fans of Blackpink, who are like a really, really awesome K-pop group. I've been part of the BTS army for a very long time as well. So thank you, Stans. I should try to figure out what cool name and kind of maybe my fan base needs to figure out what name they want to call themselves. Yeah, Blackpink in your area. Anyway, let's go back to talking about programming, right? Stack Overflow is pretty good because there's heaps of people on that asking and answering questions that will give people a chance to learn about programming. The only problem with Stack Overflow, I find, is that sometimes Stack Overflow is an argument rather than a collaborative space for people to learn about things. And sometimes Stack Overflow just has a whole lot of people trying to prove that they can do trickier things with programming than is necessary. So it's not always the best way to learn. But there are a lot of free online courses, and you can always experiment. So I hope that a lot of what I've taught you in this course has been about how to play around with code so that you can learn more about it. So regardless of whether regardless of whether there's kind of formal content or anything about something, you can always kind of pick at things yourself and push the boundaries of the particular programming language or system that you're using to see what it does. Okay, let me bring the camera back up to myself while I'm talking. I haven't used HackerRank. I actually played around with Code in Game a little bit, which is like a version of that, which is more computer gamey. We could totally call the fans Mark's chickens. I feel that'd be really funny. You can all be my chickens, and I will love you, my little fur baby back there. When people are talking about chickens nuggets as well, so like it's like heaps of stuff there. Anyway, or you could be the cheekies. Oh, there's just so many options. Anyway, I'll let the fan base think of that themselves. I'm pretty sure the fan base comes up with their own name for themselves, don't they? I don't know. So we'll see how that goes. But anyway, eventually, I hope everyone gets to the point where someone can give you an idea about wanting to do something with a particular programming language, and you can find your way through it based on the kinds of information that you've come up with already in learning about programming. Okay, let's continue along with the lecture itself, because I wanted to talk at least a little bit about stacks. I don't necessarily have that much time to do implementation of stacks, but I want to talk about it anyway, because I wanted to show you that there's not just one abstract data type, and I'll show you a different one that could be used in a different way. So you already know about the realm and the locations in the realm. They're both abstract data types. If we wanted to, we could have made locations a separate file, and we could have also made enemies a separate file. And when things get more complicated, we will often do that with code. But here, I'm just going to talk about another one, which is very, very similar to stacks, but works a different way. So a stack is a last in, first out. So basically, if you think about piling things on top of each other, like a deck of cards, if you put a card on top of the deck, and then you take a card off the top of the deck, you're going to get the same one that you just put there. So basically it builds up, and then as you take things off it,
they get removed in the opposite order that they were put there originally. So the other thing is, as a stack, like a deck of cards, you can't look at the ones in the middle. You can only pull one off the top and have a look at it. So, cool thing about this is how functions work in C. So, in C, there's actually a thing called the call stack. And the call stack is the functions that were called one at a time. So, the first function that gets called in any C program, I realize that my header thing is cutting off the text, but the first thing that's called is the main function. Matthew is saying, seems dumb, things at the bottom don't get done for a long time. It's okay, because it's about keeping stuff in the order that makes sense. So whether it's dumb or not, in terms of like when things get done, it's important that things get done in the right order. So the main will call the first function. So the first function gets put on top of main in the stack, in that you cannot get back to the main function until you finish this function 1. So let's say function 1 calls function 2. So good example of this right here. So the main calls QAdd. QAdd calls create node. So create node is here. Create node has to finish running before it can return this new node. And when it returns, it gets popped off the stack. They actually call it push and pop. So push onto the stack, pop off the stack. We pop create node off the stack. Now this is completed, and it returns the thing so that this pointer can now be initialized, and QAdd can continue running. So create node got put on top of the stack, does all its running. When it's finished, it leaves the stack, and what's on the top of the stack now is this QAdd function that can continue running. When the QAdd function finishes, it gets to the end here. It's a void, so it doesn't give any information back, but it does finish. And then that comes back here to wherever it was called, and then we go back to the main function. The main function then can call another function by adding something to the stack, and so on and so forth. So the deeper we go into functions, the more we add to the stack, and then as the functions return, the stack decreases again to go back to being the main, once we get back to only the main running. So every function adds something to the stack. The top of the stack is what gets executed. And that way, when we return through multiple functions, we always go back through them in the right order to get back to the main. So I just wanted to talk about that a little bit. It's not, you don't have to fully work with the function stack, even though you have been. Every time you've called a function, you've been working with a stack without knowing. I love it because it's a really cool system, right? It's a simple system, and if we have something that just says, all right, pile these things on top of each other, and you can only run the code in the one at the top, then we get this clear, logical function system that says you go into a function, and when you come out of the function, you go back to the one you were at before. There are other things that we could consider for stacks, stuff like the back button in your browser always goes back to something that you're at before. So if you're just surfing through the internet and you're going through looking at different things, going through the back browser is like going through a stack of the places that you've been. And then when you go forward again into something else, it builds the stack up again, so when you go back, you could still go back past things. So it's an interesting data structure that's actually used a lot in programming, and we can think of it as something to simulate like a deck of cards in a game like that as well. Liang said time for recursion. Yeah, unfortunately, recursion is a concept, and it's a cool concept. It's really useful in certain circumstances. It's where a function actually calls itself. So the function could keep calling itself until the point where one of them returns, and they will cascade back through returning them all. We're not going to teach you the full concept of recursion like it's a concept. Like, I would love to spend a whole week on recursion, but we're out of weeks. But you can look it up and you can learn about it. You will definitely learn about it later on. I think that, if I remember correctly, it'll be one of the 2.5 subjects where they start talking about algorithms and stuff like that that will go into recursion. What's that? Oh, did Dean? Dean was the one that started talking about recursion. Yeah. Anyway, let's not get too sidetracked. I want to teach you about stacks, not recursion right now, because I haven't prepared any content about recursion. Okay. So we're going to think about this as an abstract data type. What kind of functions would we like to see in a stack? We want the create and free, right? Because we're always using create and free for things. And then we're going to call these push and pop. These are the technical terms that people use for them. Push, add something to the top of the stack. Pop, remove something from the top of the stack. Sometimes we want to just look at the top of the stack without actually removing it. And also, we might want to look at the size. Same thing as the queue. We don't want to be able to pop from something that has size 0. So we can, if we want to, check the size first. The same way that we were checking if the queue. Obviously, doing this full implementation at this level for the queue took us 2.5 hours. We've only got half an hour left. So I'm not going to go through all of it. I will look at some of it. Oh, Dean, you are answering a question someone asked about recursion. Yeah, right. That's okay. That's fine. Oh, I should shrink myself back down a little so you can see everything. Okay, stack header. Looks very similar to a queue. In fact, looks nearly identical to the queue. The only difference is some of the words are different, but a whole lot of these functions are going to look identical because from an abstract sense of a collection of objects that you can add something to or remove something from, most everything you're going to do in it is the same. The only changes that we're getting here are going to be on how it behaves. And how it behaves is determined by what rules did we decide for how this thing works. It is a last in, first out, not a first in, first out. So the queue was first in, first out. This is last in, first out. So we are going to implement these things differently, but the interface to accessing this thing is actually going to be reasonably similar. So, what's our internal structure? Now we could very easily use a linked list again. Now for the moment, this is kind of a choice between two, because I've only taught you two ways of organizing collections of data at the moment. When I'm talking about sort of unending collections of identical data, which is kind of what stacks and queues are, not necessarily unending, but a linked list could be considered to be something that just doesn't end until you run out of memory. So we could use a linked list, or we could use an array. It doesn't matter which of these we're going to use, because whichever one we end up using, whoever's using the main.c will just see the stack, and they won't know what's happening underneath. So we used a linked list for the queue. I'm going to use an array for this just to show you that in a sense, the decision of how to store the data is based on who's going to implement it and how they're going to go about it. Okay. I don't think there's anything in chat I need to look at right now. Okay. So let's try this in an array. And so what we're going to do with this array is we're going to track where the top of the stack is. So this is going to be my stack, and the bottom of the stack is going to be the first element of the array. And then I'm going to have an index which measures where the top of the stack is. So it says, okay, I'm going to have the index which is going to, do you remember this? Do you remember arrays? Do people still remember arrays, or have they like disappeared out of your head? I hope that arrays have not just like yeeted off and you still know how to use them, right? So we have 5 elements in the stack, and then we have index number 5 here that says, okay, here is the next thing off the top of the stack. You know the beauty of this, right? This index here saying this is the next space that we could add something to the stack. This number is exactly the number of elements that are in the stack at the moment. So I'm just like, this is beautiful. I don't even need that separate size integer that we had before. If I'm tracking the top of the stack, I know how many items are in it. And then we have the rest of the array that we may use if the stack grows larger. I've colored these orange. There will be numbers in here, but we don't consider any of these numbers that might be in here to be valid, because only the numbers that are in the stack are valid. Everything else we consider to be empty memory. Even though there's always going to be ones and zeros in that memory, we're going to ignore them because they're not the stuff that we actually stored. So we've got this empty space that we're going to use later. This is kind of the difference between an array and a linked list. The linked list is never going to have these chunks of empty memory waiting. They will allocate the memory as they use it. Whereas the array has to be a fixed size from the beginning, so we're going to kind of have all this array to begin with, and then we're going to use it. So, some code lets us... I'm going to close all of my Q stuff. And here's some stuff that I prepared earlier. So here's the main and a stack.h here. So let's just open them. Okay, so this is adding... So I did a deck of cards here. And we're going to add things to the top of the deck of cards, and then we're going to take cards off the deck of cards. And we have the H file here. So the next thing we're going to need is a C file for the stack. So implementation of a stack based on stack.h. Each element stored is an integer. I'm pretty sure it's an integer, right? Let's look at our h and say, okay, when we're popping something from the stack, we're getting an integer back. When we're pushing something onto the stack, we're storing an integer. Okay, good. That's fine. What are we? Oh, we're still in July. We're only just still in July. We are always going to want to include the H file that we're implementing, because if we don't include that, then we don't know what the functions are that we're going to be working with. So I said that we were going to work with a reasonably large array that would be able to store stacks that we think are feasible for what we're doing. So I'm going to hash define a maximum stack size. I'm just going to call it max stack, because max stack sounds funnier than max stack size. Okay, I'm going to make this huge so that we're unlikely to hit that limit while we're using it. If I know that I'm really only going to be testing this with 3 cards at a time, then maybe I wouldn't need as much. Or maybe I know that my my deck of cards is a standard deck of cards that only has 52 cards in it. Then I could say, let's have 53 just in case. So I could say that's the maximum number of things that I expect to be in this. But, you know, it's much of a muchness. If I want this thing to be generically useful for a lot of different circumstances, I probably don't want to limit myself to something that low. So I'm going to make it 1024. You know those programming numbers that we love? Divisible, like the powers of 2. So we're going to go with one of those. And then we're going to have a look at this and say our stack internals is a struct that has an array in it that stores all of the elements of the struct. So now we're not even bothering with pointers. Because we're using arrays, we don't need pointers. We're just going to have the array inside the struct. I just saw that same thing again. I'm just going to fix that. Okay, so it's a struct, and we called it stack internals. Let me make sure. I did the same thing here, where I think stack internals, yeah, is in camel case, and I wrote the comments in snake case. So stack internals. So that's bad code style there. So I've already lost my potential maximum code style marks for the code I'm showing you. I think it's important to see that, like, you know, I may be lecturing you, but I'm still human, and I'm still going to make mistakes, and we're all going to be making a lot of mistakes along the way. Code is not something that humans do without making mistakes. It's more about figuring out how we deal with those mistakes and how we fix them than trying necessarily to do something without ever making mistakes. This is very difficult. Okay, so we're going to have an integer array, and I think we're going to call it the stack, right? Did I do that in my slides? Yeah. Because this is actually the data that's the stack. And it's going to be of size max stack. So that means that what I'm saying is when I create stack internals, when I create one of these, it's going to, as part of what it is as a struct, going to have an array inside it that has 1024 integers worth of space. I'm not necessarily going to use it all, but it gives me some headroom if I need to. Then I'm going to have an index. An index is just an integer, if you remember, between 0 and 1 less than max stack, and that will be able to address all of the elements in the stack. And I'm going to call that top, because that was the name for it. It was the top of the stack. So it's going to tell me where the current top of the stack is. All right, so if we're going to create a new stack, all we're going to do, so we have a type def that says a stack internals pointer is also a capital S stack. So if I want to create a stack, I need to return a stack internals pointer or a capital S stack, same thing. So let's go stack create, copy that. I'm gonna say create a new stack and return a pointer to it. I'm going to say a new stack internals because I want to be clear that it's this structure that we're building. So if we're going to make a structure, we're going to allocate some memory for it, and then we're going to return the pointer to it, which is the stack. So I can say stack. So if I want to here, I could call it a struct stack internals pointer. Actually, I might. So the naming scheme often is we will often use the struct name inside the implementation, and then obviously out here in the main and the H file, we'll use the abstract. Because when you're viewing it from one perspective, it's an abstract, but when we're viewing it from inside the C file, it's more of a definite than an abstract. So I'm going to say, just remember that this is actually a pointer to a struct. Let's call this thing new stack, and we're going to memory allocate the enough memory for a struct stack internals. All right. We should be getting used to this line of code now, right? So we are going to, we're always going to be taking the size of a type to put into malloc, and that same type is going to be the type of the pointer that's returned from malloc. Oh, Dean and Tom are there. All right, so I'm not gonna. I don't need to answer everything that's happening in chat. People are joking about my level of humanity. What is the problem, students? I am normal human. I am teaching unit number 01. Anyway, okay, so wait, someone said stack create should have a void. Not necessarily, no, because if it's going to create it, it needs to be able to give back the pointer to the stack that it's creating. We don't actually need to put a void in here if there's no inputs to a function. So if we want to, we could put a void in there in the same way that int main void always has a void in there, but I'm not even sure why int main always has a void in there. I'm pretty sure if we deleted that void, it would still work, but I can't necessarily. I don't actually know the background reasons why, but I know that when we're having functions that don't have an input, then we can actually get away with just not having an input. Okay, so I've created this new thing here. I need to check if I need to initialize any of these. So the array I probably don't need to initialize, because any of the uninitialized information in there I'm not going to use. I'm never going to be reading this array I'm only going to be adding or removing things in this array based on where the top is, but the top needs to be set. So new stack inside the struct has a top, which is an integer. I'm going to set that to 0. So I'm going to say that the stack is currently empty and the top of the stack is the very first element of the stack. Oh, there's a lot of talk there, but I'm not sure if I need to read everything. Dean's saying that for correctness, we probably should have a void. So let's go with that. I think I get used to not using it because I know that it'll still run without it. And if you notice, the queue example worked fine without me putting the void in there. So it's a matter of choice. Unless someone knows the actual technical reason and if there is actually a difference between void and an empty gap there, I don't actually know myself. I've just sort of used it without ever actually really looking at the technicality behind it. Okay, so I've created the stack there, and then I'm going to return new stack. So it's pretty simple, the creation of a stack. I've done the same thing there. And so let's push and pop onto the stack. I've got some diagrams here to let us know how it's going. So if I want to push the new element 82 onto the stack might start with some elements in it. It might not. This one's not as picky as a linked list, because if top was 0, it would just be aiming at an empty space where we could put something. So what we're going to do is, the top is here. We're going to, whatever is in there, we don't care, because that's not data we care about. We're going to override it with a number, so that if it's the 82 that we're adding. And then that would then mean that there are now 6 elements in the list, so the top moves to 6 after that thing has been added. So this should actually be pretty simple, this code. So we've got stack push here. I'm going to go in and actually do it. What's happening there? My gedit could have just been lag. So here's my stack push. Going to grab this function. And write this. So I'm not going to be able to do a full implementation today, but I'm at least going to get the push and pop going. We probably don't get the freeing. Actually, freeing's really, really easy for this, because this struct doesn't have any pointers to any other memory. So in terms of the chunk of memory for this structure, it's actually a really, really big chunk of memory, because the entire array is inside the structure, as opposed to a linked list where the queue internals was really small and the pointers were aiming out to other memory, which means you had to follow those pointers out and clean the other memory. Whereas if we're cleaning stack internals, I can write this really quickly here. Well, really quickly, depending on what's going on with VLab right now. So let's copy stack free. Paste this here. That's it. Because the stack internals actually contains all of its memory within itself, so you just free the stack itself. So a stack is a stack internals, you'd free it. That's it. So yeah, we don't have to do as much complicated stuff with it. There are arguments either way for using arrays versus linked lists. The linked lists are more flexible. They don't have an arbitrary limit somewhere, and also they only use as much memory as they need as they're going along. So if we want to be really efficient with these things, the stack is super inefficient because it's just grabbing this massive chunk of memory whenever it starts. And then it's always there, available for it, which means it's always kind of wasted for anything else in the program to use. But also it has a limitation where if you try to add an element beyond that number, then it won't work. So, pros and cons. It's easier to think about and easier to work with because it's an array, but it's not necessarily as flexible. It's not necessarily as good for the computer. We always go back and forth. There's going to be a constant struggle back and forth. And so this is me talking about the future, by the way. This doesn't have to be how you think about your computer science right now. Right now we're thinking about how do we solve problems. And I want this entire course to be focused on how we solve problems. Later on in your computing career, you will know how to solve problems, and then you'll be wanting to look for the best solution. And there's different solutions, and each of them has their pros and cons. And there's always a seesaw that goes back and forth between using more memory and using more processor. So the more processor you use, the more amount of time it takes for something to happen. The more memory you use, the more memory resources you need. And it usually goes like a seesaw. So there's a lot of things you can do that take more memory and that take less time to run. And other things that use more computational power, but they don't need as much memory because they recalculate things as they go. You'll learn more about this as you go along. I mean, this is actually something that I don't think I really got a full grasp on this idea until after I'd finished my degree and I started writing, I guess you'd call it, no, it's not quite commercial software because we were doing research and stuff, but writing software and trying to figure out what our needs were and whether we needed to optimize things for speed or for memory usage and stuff like that. Anyway, side note, not super important right now. Okay, so the stack push, let's go back to that slide, is going to say, where is the top? I'm going to overwrite the element where the top is, and then I'm going to move the top. So hopefully this is not going to be very difficult. Add an item to the top of the stack. Uses top as the index for the new item. So we've got the stack S. We look into the stack S and we get its stack. I should not have named that. That's a really, really bad name, because we've got capital S stack and now we've got small s stack, and when a human says it, they say the same thing. So it's gonna cause a lot of problems. In fact, I'm gonna change this now before it becomes a bigger problem. I'm gonna call it stack items. So it's gonna be the array of items that are in the stack, as opposed to saying it's all of the stack. It's not all of the stack, it's only the items. And this way I should be able to remember it a little bit better. So this is the array, and the index that I'm looking for in the array is the top of the stack. So this here is how I access this box here. So I say, get me the array, use my square brackets, and then use the number that top is to address a certain element of the array. And we're going to say, don't care what was in there, we're overriding it with what item is. And then we say stop plus plus, which means we move the top further along. This is going to work most of the time. I say most of the time. There are still issues here. So there are potential issues if, say, for example, top is 1024. If top is 1024, then we've got a problem. We've run out of space in the stack. So we probably would want to check for that. So I can say if, and I'm going to say else here. Because definitely, if I think that this thing might fail, stack has used up the whole array. So if top is, I'm going to hedge my bets to make sure. So I could say if top is equal to max stack, then I've hit the end. But I always prefer to do greater than or equals to, just in case something goes wrong elsewhere and this number goes much further than the top of the stack. Then we've used up the whole array. We're in a lot of trouble because we just can't add something to the stack at this point, and our stack is no longer functioning because it's hit its limit, so it can no longer accept items. We don't have a return, so we don't have anything that we could say back to say that stuff is broken, so we might kill everything here. So I might say, let's print F. If I'm going to print F, I'm going to need to... Ooh, another thing I'm going to need to include is the standard library, because without the standard library, I can't do any of that memory stuff that I was doing. I'm going to do standard input output as well, so I can do a printf. So let's printf stack has run out of space, cannot push another item. Just a quick little error message there, and then we're going to blow up. So we're going to say, I don't like this anymore. We're going to have to end it here. Oh, were there any questions there? Oh, Lucas is asking, is this where this term Stack Overflow comes from? Yes. It's an old school kind of thing, because there used to be the ability, like, you could fit a program in a certain amount of memory, and then the stack, you know how I was saying the stack, the call stack of all the functions you could call? If you kept calling functions up to a certain point, or you called massive functions that took up a lot of stack space, it would pop off the top of the stack, and then you'd run out of stack space, and the error is actually called Stack Overflow. I don't know if that's a C error. It might be a C error or not. Yiji is saying it's behind you. What's behind me at the moment? Have I made a mistake somewhere? The if-else mistake? Did I do it somewhere else? I'm not sure. Let me know what the mistake is, or watch me flounder as I look for it. Oh, S-top. 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 There we go. By the way, this is what happens when a native... So this would be like if I was lecturing you and I didn't speak English as my first language. Every now and then I'd say a word that just sort of didn't make sense, but you'd be like, I get what he's trying to say, but that wasn't the right word for it. This is what happens when a native C++ developer teaches C. So in C++, you can get away with this. It actually means something. Because the variables that belong in the struct are accessible in the entire file in this case. Oh, Roy's saying I didn't include standard input output.h. Have I? I thought I added that, but I wasn't sure. I did, it's okay. Yeah, so as I added the standard lib, I also included standard input output. You'll find a lot of people's programs just include both of those all the time. It's not the best practice if you're not going to use them, but like chances are you're going to use them in nearly every C program. Okay, so now we know that if we hit the limit, we will stop. So this is our push. It's going to be pretty easy, right? We replace the item that we can see at the top location, because there isn't an item, and then we move the top location upwards. Let's look at popping, and we'll implement both of those, and then show some testing of that. And I think that's probably where we're going to run out of time. Okay, so the push code was like that. The pop does the same thing in reverse. So the first thing that push did was it set the element, and then it moved the top. This one does the opposite, so it moves the top back down one first, and then reads the element there. So note here, I've colored this in orange after I've read it. I'm not actually wiping this memory. I'm not making it not mean anything. In fact, if I want to, I could say this. I probably shouldn't edit my slides to make an example, but the 8 is still there. But I don't consider that to be part of the stack anymore. I have read the element, spat it out, but if I add something to the stack now, it's going to overwrite the 8, and the 8 will disappear. So the 8 is still there, but I've colored it differently because I consider these things to be in the stack and everything out here to be outside the stack, and it can have values. But I don't care about them because the only way I'm going to get up to here in the stack is to overwrite anything that's there. So that's why I actually had the 8 disappear, even though in memory it is still there. It's totally still there because it's in an array that I've declared and it's the value I left there. But in terms of the stack, I will never use that 8 again. Okay, So even if someone put 8 in, I would overwrite this 8 with a new 8. So let's look at this. We're going to move the top down, and then we're going to read the element from there. So let us come through here, and we have stack pop. Stack pop is going to give us an item that was on the stack. Return the... Let me just scroll down a bit so you can see this more easily. Return the item that's on top of the stack. Move the top down 1. Okay, so again, we're going to have this potential issue that we could have had before, where if the top is, I'm going to do less than or equal to, just in case something really, really full on has happened. Oh, it's behind me. If the top of the stack is less than or equal to 0, it means there's no items on the stack. Stack is empty, cannot pop. Just can't pop. Only locking, no popping. Printf, stack has no elements and cannot pop. I just want to say cannot pop because it sounds funny. Okay, stack doesn't pop. We're also just going to let this thing go at this point because there's no integer we can return that would make any sense there. So if the stack does have elements in it, we can then do something. So what did I say? We were going to move the top down 1. So top minus minus, so it moves down 1, and then we're going to read whatever is in the top. Let's create an integer before we go into an if-else's. Stack item. And then we say stack item is equal to s stack items s top. So again, that's the same line as we had here to access the current top. And the current top now has moved to an actual item there. And we can come out here and return stack item. Now, if I wanted to, I could have done this really, really shorthand. And I could have not created the temporary variable here that I'm using. And I could just do this. I could just return what I see there. You can do this. I mean, it's like there's always an argument back and forth in terms of style on whether to do this. A lot of people like to make sure that because this is a function that returns something, that the very last line that you can reach in it is the return that finishes the function. So it finishes at the end where the brackets finish, and then it's easy to know that this thing is complete. Because all possible paths through this function are always going to lead to being able to return something. So even if you don't know anything about the complexity that's going on in there, you can always see this. Having the return statements inside ifs and elses mean you have to look really carefully and make sure that every possible path through this function actually finishes. So that's the reason why I actually went to the trouble of adding extra lines, putting this stack item here, and setting it to this value and then returning later, because sometimes it's just easier to read when we do it like this. I mean, I've seen plenty of people do it the other way, and I've already got this potential issue here where I am ending this function and, in fact, the entire program before it reaches the end. So there's still, there's still ways that this doesn't read that well, but sort of. I can sort of make this really, really clear that no matter what happens in here, this function, if it makes it to its end, will return an integer. There's a lot of arguments back and forth about how we should style these things, but I try to, as much as possible, keep these return statements right at the end to make it clear that this thing is definitely returning what it's supposed to return. Okay, So with this, I'm well past the point where I should have compiled this to see if stuff works. Like, how many functions do I write? I just wrote like 4 or 5 functions without compiling. So this is like super, super dangerous. Let's go and compile this now and see. I mean, also I have 1 minute left. So, oh wait, someone stop me. Where did I use? Did I use top in the wrong place? Everyone's saying it's behind me. So, stop max stack exit 1 s stack items s top equals item s top. Wait, no, that's push. Sorry, it's somewhere in pop, isn't it? There it is. I don't know how many times I need to talk about the same error just to continue making the same error. I guess it's like, like I've got friends who have been living in Australia for like, 15, 20 years, but some words they will still say in a direct translation of the language that they learned while they were growing up. And it's the same thing that I'm doing here. I learned C++ when I was growing up, and then I switched over to doing C development, but there are ways I will just still say stuff that's that's in C++. Okay, let's just clear this for a second. Oh, we haven't compiled this stuff at all. So we're going to DCC the main.c and the stack.c, and this is going to be stack demo. Ah, it compiled first go. I wrote 5 functions and it compiled. That's either amazing or very, very bad. Let's see. Let's run that. Hey, it did work. So 42 goes on top of the deck. 37 goes on top of that. 13 goes on top. Then you take off the top of the deck, you get 13. Take off the next top of the deck, you get 37, and then 42. So this stack is functioning correctly. So I'm going to quickly run through the rest of the slides. What would we do if this was the linked list? Now, there's other ways we could do this. We could have the top pointing at the head, and we could just add and remove to the head of the list. Or we could add and remove from the tail of the list. It doesn't matter so long as the rules are followed. You can use your data structure however you want. So I've actually got a linked list implementation, which I don't have time to actually do, but you could see how I could have a node, and I could have a pointer to the top of the list, and then I could push and pop by adding a new object to the head of the list, and then removing the object from the head of the list. I don't really need to implement this for you because a lot of the implementation of this is the same as how we implemented the queue. So the point that we're getting to is that whether I implement this as a linked list or as a stack, I didn't have to change the header, and anything using the main function wouldn't have to know the difference. I'll probably give you the code for linked lists as well, so you can see the difference, and you can swap them back and forth if you want to. So I don't usually go all the way to the last slide. I just leave that for revision for people. But one thing I did want to say is that, okay, so we're talking about abstract data types. You're not necessarily going to need to build them in COMP1511, but I would suggest it's a good thing to know about because you're going to get to this later. But the other point I would say here is we are now at the end of new content for COMP1511. We still have lectures and tutes and labs next week, but everything next week will be dedicated to a complete recap of everything we've seen in the course, so some detail on everything, and some things that I can say now that you know everything that I couldn't say about certain topics as I was slowly building up your knowledge. And we're going to go through what the exam is going to be like as well. So what the question format is for the exam, I have a 99% sureness of exactly how many questions there are in the exam and what type they are and the level of difficulty that each question is and stuff like that. So I'm going to tell you all of that and that'll be next week. But if you have any questions about the exam, you can always ask them on the forums and stuff. The answer might be just wait for Mark's lecture; it's coming. But some other questions might be answered, like just like what's the logistics of it, because we have a start time, and an end time. We know how long we expect it to be, and things like that. But for the moment, Leon's asking, in a normal exam, would you have pen and paper? Yes, you do. So if you were doing a sit-down exam, a locked-in exam where you have no internet connection or anything like that, so you can't look anything up, you're still allowed to draw pictures, and I highly suggest that you do that. I rarely work with linked lists without drawing pictures. So either I've got my diagrams, which I've done already, or I've been opening up Microsoft Paint and just drawing them, because it just makes a big difference in terms of your understanding. Okay, apologies, I've gone over time again, but I just wanted to say, yeah, that's it for the amount of content we're going to give you. Over the next week, when we do all the revision, we are also going to open up a part of the course website called Revision, and that has a whole bunch of like old questions that cover all the different topics that we've covered. So these are questions that most likely, I don't know if any of them, some of them have potentially been used in weekly tests and labs and stuff, but heaps of them have not been used in weekly tests and labs, so they're pretty handy if you want fresh questions on particular topics to test yourself or do revision. And a great number of these are past exam questions as well, so they should give you enough kind of preparation. In fact, a great deal of the weekly test questions are past exam questions also. Next week's Tutes and Labs will have they're going to have questions that are simulated exam questions that give you an idea about what kind of things we might ask in the exam. So I should wrap it up there, because I've gone over time. I apologize. I'm going to go into break mode, have a quick break, come back, and answer any questions that people have in the chat. So we'll end the official lecture here. All right, see you in a sec. Alright, we're back. And I thought I'd point out, when you're saying, he's behind you! Chicken was actually behind me the whole time. She's just been sitting behind me in the chair here while I've been teaching. So this is what it's like when she's well fed. She's like, I just want nap time, right? As opposed to when she hasn't been fed, where she's like, feed me or die! Okay. Did we have any questions? Anyone needed to ask any questions about abstract data types or anything like that? Or if you want to look closer at the code that I didn't actually implement, like the stack linked list code. The stack linked list code has a significant amount of copy paste from the queue. Because if you look at it, if we're going to remove, if we've got a pop where we're going to remove the head of the list, straight out copy paste from the remove from the queue. Adding to the queue is the only thing that's different, because we'd add to the front of the queue rather than the back of the queue, which is easier because you only need a head pointer. You never actually need the tail pointer then. Yeah. So, if anyone has any questions, feel free to ask questions now. I have a feeling that there's probably not that many questions because people were asking. We were actually covering all the questions live this time as we were going, and I think that Tom and Dean both having two people here answering questions means a lot of them were answered already. But I will stick around now just in case anyone does have any questions, I will stick around for another 30 seconds or so. Give everyone time to type something in if you want to type in anything. If not, I will head off. Also, I'm just gonna go back to chicken cam. Jed's asking if the exam is in VLab. The exam kind of can be in VLab if you want it to be, in terms of like the auto tests can be accessible via VLab. But if you've been accessing our computers via another method, so there is the whatchamacallit, some people are using SSH, some people are connecting via Visual Studio Code and other things like that. All of those different ways are still going to work. So it's going to be similar to the way you'd work on labs and assignments. It won't be very much different from that. So you can kind of trust that everything that we've been getting you to build up the capabilities of doing, we're going to be testing that. We're not going to put you in a different environment entirely. It's only if you're doing face-to-face exam that we would put you in a completely different environment where you don't have a web browser and stuff like that. So the face-to-face exam would be like purely what you know and nothing else. Whereas a take-home exam examines you in a slightly different way, which is actually more realistic, which is like, when we're programming, we usually have an internet connection. So we consider our entire skill as a programmer to include our ability to look things up and our ability to learn things quickly and then implement them, rather than what we've memorized. You still need to memorize a fair bit. You still need to kind of understand your concepts of what you're doing well. But you can go back to your references and look things up. So Tom's asking what questions will be on the exam. There are many questions on the exam, but all the questions are going to be related directly to content that we've done before. They're going to be in the same kind of escalating scale as we've seen both in assignments and labs, and weekly tests, where anything that's earlier in the questions is going to be easier, and what I would consider to be more important fundamental knowledge in the beginning. And then the later you get, the more things you'll see that are trickier, kind of slightly weirder ways to use the data and things like that. So it's kind of like what you need to know, what's good to know, and then can you then take what we've taught you and extrapolate into more difficult things. So that's the way that we're going to be structuring the exam. In terms of the actual questions, the number of questions and what's in each one, we'll spend time on that. So we'll do the lecture on that next week. SK is asking, are linked lists or arrays more efficient, or does that depend on the application? That's a big question, and it does depend on the application, and it also depends on your definition of efficient. So your definition of efficient might be, does this thing return information with the least amount of CPU cycles necessary to make it happen? In which case, often arrays are quicker because they're directly addressing memory. The way they're lined up in memory next to each other means that you can grab more than one element of the array at a time, and then scan through them. Linked lists, you have to grab one piece of the linked list, and another piece might be over here, another piece might be over here. But a linked list is more flexible, right? So the linked list is more flexible because it only uses just enough memory for what it needs to do. So hard to say which one's more efficient. It depends on the purpose. So I would definitely say that the stack there that I did that had like 1,024 elements available to it and it only used 3 of them, that's really memory inefficient, but it might have been processing, adding and removing things faster than the linked list queue implementation. So you choose which efficiency you're going for at that particular time, and then you'll know which data structure to use to be the most efficient. So huge question, right? And like there are people whose entire entire profession in the computing industry is to look at other people's code and try to make it run in a different way. So, for example, this is a huge game industry thing, right? The Xbox or the PlayStation has a really particular architecture in it. You always know that you have an exact amount of RAM, you have an exact amount of cache on the processor, you have an exact graphics processor, you know exactly how they work. If you're good enough, you can take other people's code and make it so it still does the same thing, but it fits everything exactly into the capabilities of the hardware, and then it runs much better. It's a hell of a job. It's a really, really tough thing to do. Because you're playing this weird balancing act between how fast the hardware runs and what you can do with it while still getting what everyone needs to happen. So a lot of people don't even bother because you could always just ease back on the technical requirements of what you're doing, and then the PlayStation will just chug along at 50% capacity and it will still run everything that you need to do. But some people who try to get the maximum out of things will go to a great depth to do this. Basically, the people who are building things like the Unreal Engine and stuff, there are several people there who will be like, nitty gritty, looking at little blocks of memory and how to move them around. The scariest thing I've ever seen is someone for a computer game level. At the beginning of the level, they mallocked like a gigabyte of memory. So they just malloc a gigabyte of memory. They didn't do size of a particular variable. They mallocked the memory and then they manually indexed where they wanted everything to be, and then everything they accessed in there was just manually indexed to the right locations. And it was like, that's really scary. Just one typo and you're just off in memory somewhere and you don't know where you are anymore. But that's how they were doing it. So, there's depths to plumb there if you want to in terms of efficiency. I like that question. I always like any question that sends me off on like interesting things to talk about. Okay. Okay, so that was a question about linked lists or arrays being more efficient. Jeffrey's asking you about guidance for the assignment. My suggestion, if you want guidance for the assignment, is right now there's a help session with Dean. So he's already gone off to the help session. He would have gone at 6 when the help session started. Chances are there's not too many people in there now. We don't know. I don't know. I haven't been checking. I have noticed that some of the help sessions have had a lot of people in it. So I would suggest go talk to Dean or whoever else is there. There's probably multiple people on the help sessions now that we're getting to crunch time. So you should be able to get some help there, especially if you're asking about the assignment and you want to be able to show your code. If you show your code here and now, I mean, you can't because we're not really set up to do this here in the stream. But if you did, then we'd have an issue because everyone else would have seen your solution code. Jed's asking if the exam will have stacks. There will be something about stacks in the exam. It won't be that full on. Like, we won't necessarily need you to build it from scratch with multiple files and the abstract data type or anything like that. But we might ask you questions that see if you understand how to use them, and like the idea that a stack is a last in first out, and so what does that mean for the data that gets used. So we might ask you questions like that. Jeffrey's saying the help session is pretty popular today. Yeah, there might be a lot of people there. Priya's asking if there will be auto tests for the exam questions. Yes, there will be auto tests for the exam questions. They will be scaling. There will be more and more comprehensive tests for earlier questions than there will be for later questions. If you get up to the later questions and you want to solve the later questions, to get the full marks for those, you have to know how to test your own code. So there's always that level of difficulty going on there. Wei is saying, sorry Mark, I'm still confused by the AT. Don't ever apologize for that. There's no worries at all, and I fully understand if stuff is confusing still, because, I've barely had 4 hours to talk to you about these things, and I would never really expect someone to fully grasp something with only a few hours of looking at it. So, no need to apologize at all. You understand it this way: linked lists and queues and stacks are ADTs. To achieve the goals, we use the functions defined in the .c files. Okay, subtle difference here. A linked list is not an ADT. A linked list is something I would call a data structure, which is very, very specific about how it joins things together, about how it sits in memory and things like that. An abstract data type is something that has a vague set of rules. Oh, it might not be vague. It could be a really specific set of rules, like first in, first out. But it doesn't say how it sits in memory. It doesn't say anything about how the pointers join it together or anything like that. It's an abstract, which is an idea, not a concrete implementation. And that abstract idea will be presented to other code in an H file. And this H file, as you can see, does not tell you any information about what the internals are other than the fact that internals exist. So the closest thing you're going to get to the internals is knowing that there are internal workings. But otherwise you just use it and you expect it to follow the rules as you use it. So that's what the H file is. The H file is the interface between the code that uses it and the code that implements it. And the C file is where all the details are. The C file is where the decision is made on what the internals of the stack are versus, let's say this is an array, but it could have been a linked list, or it could have been some other data structure, right? So it could have just been something else. So the H says what the functions should be called so that the main can call them and then the C can implement them. So the implementation file, C file here says, okay, this is where we actually do the work that makes stuff happen. And the H file here is, this is where we say what should happen but not how. So hopefully that gives you a bit more information about how an ADT works. So I think you were just slightly mixed up there between the H and the C file. So the functions were defined here in the H file, and the C file is we hide the implementation. Yeah, because the C file here has a struct, and we notice here that the main can include the H file but not the C file. Yeah, cool, great. Glad you got it. Right. I think that's it for today for the lecture. So that's it for the questions. So that's good. Glad everyone is happy with what's going on so far. And also there seems to be people going to the help session, which is good. I mean, like, if you're unsure about things, going to the help session to get help about things is good. Oh, Jeffrey, it's a wait time of an hour. I'll ping a few other tutors and I'll try to get some more tutors to join in at the help session, because an hour is a long time. And if there's too much of a problem, talk to your tutor this week. I mean, you may already have had your tute, and so you may not get that chance. But I will ping some other tutors now and see if I can get some more people to come and help, because we kind of going to want more help there, I think. Jeffrey, oh sorry, what is your estimate? That was your estimate for how long it was going to take, or the actual? Oh, there's 14 people. Yeah, but even then, I'll check how many tutors we have, because if we've got like 3 tutors and 14 people, then it's no big deal. Like, they'll get through it. But if we've only got Dean and there's 14 people, then yeah, it's going to be an hour. So we'll check. I mean, Dean knows. He's been running stuff like these help sessions for several years, and so if he needs more people, he'll buzz some people and get you some help. So hopefully he usually doesn't leave the help session until everyone's been seen anyway, and if it can't happen within the time frame, he'll get some help in. So chances are should be fine. Hopefully you get the conversation that you need today, Jeffrey. Okay, I will wrap up the lecture there, and I will see you all next week. Good luck with the assignment. I will be at least watching a little bit and getting reports from the tutors about how the help sessions and things are going, and we'll try to make sure that everyone gets the help they need to learn stuff. Yeah. Oh, thank you very much, Jeffrey. Jeffrey's just saying that he really appreciates the the amount of help that's given in the course. I mean, especially in this kind of online world, like we would expect people to get more face-to-face help, and face-to-face help is like you can't get better than that. Like someone sitting next to you with your computer, talking to you about it and saying, okay, this is what I would do in this situation. Here, let me grab a pen and paper and I will draw some stuff for you. I'll give you the drawing and stuff so you can keep it for later. You know, all that kind of stuff is really, really useful. And we're just sort of doing the best we can to simulate that now. But I know that like we do need to have stuff like lab time and help sessions where people can get one-on-one, because we need to make up for the fact that the quality that we would usually present at is face-to-face. So because we can't present at that quality, we just put more time in and hope that that balances at the same level. And I think it's working mostly, but we'll see. We'll see how everyone goes by the end. I forgot to remind everyone that there's actually a course survey as well out, and then we'd like everyone to actually fill out the survey, give us as much information as you want to about how the course went for you, and how you might, if you wanted to change anything in the course, what would it be, and how the online learning experience has been. But I'll put a notice out about that over the weekend to just remind people to fill out the survey if they can. Anyway, thank you very much, everyone. Thanks for sticking around. I will head off now, and I will see you all on Tuesday.